Okay, so we're going to go through some conservation of momentum questions. Um, and our basic momentum formula is P is equal to mv. P is the symbol for momentum, and then m is mass, and v is velocity. And mass is usually in kilograms. Velocity should be in meters per second. And now when you're looking at these problems, you have to kind of look and say, okay, normally with momentum problems, and especially conservation of momentum, what I'm looking at is that my beginning momentum is going to equal my final momentum. So that's what they're talking about, is conservation of. So if I start off with a momentum of, say, 10, and something happens, if momentum is conserved, then you should have momentum of 10 when you're finished. So let's take a look at this problem we have here. A 1.2 kilogram block and a 1.8 kilogram block are initially at rest on a frictionless horizontal surface. So that gives us some interesting information there, and what's mostly interesting is that our P original or initial is equal to 0, right? Because it's at rest, so that means that these two blocks, they're connected with some sort of spring here, it looks like. They're not moving, and so therefore no momentum. And then when a compressed spring between the block is released, the 1.8 kilogram block moves to the right at 2 meters per second is shown. And we want to know what is the speed of the 1.2 kilogram block after the spring is released. And so since we know that the beginning momentum of the system, and that's this block and this block, the whole thing equals 0, then we know that we have to get a number at the end after it's moving. It still has to equal 0. And so essentially this is how we'll set this up. I know that my original momentum was equal to 0. And so we're going to say that 0 is going to be equal to 0 for my final momentum. And so when I do that, let's take a look at what happens to this block that's moving. I have a 1.8 kilogram block that moves 2 meters to the right. So momentum formula says that 1.8 kilograms times 2 meters per second, that's going to equal 3.6 newtons seconds, right? So that's our, and that's what's happening to this block here. Well, the block here and the block here, when I combine the momentums, they have to equal 0. So this tells me that whatever I have on this block, it has to equal negative 3.6 newton seconds, because when you add the two of them together, they have to equal our original, which was 3.6. So this makes this problem fairly straightforward. We can say for the second block, since we know that its momentum has to be negative 3.6 newtons per second, or not per second, but equal seconds, we can just take its mass of 1.2 kilograms and multiply that by its velocity, and then just divide out, right? So 3.6 negative divided by 1.2 means that we have a velocity equal to, looks like 3.0 meters per second, negative 1. And then it would be going in this direction since it's going to be negative there. So, and then let's try this next one. For this one, I have at a circus, a 100 kilogram clown is fired 15 meters per second from a 500 kilogram cannon. And what is the recoil speed of the cannon? Well, again, this is a momentum problem that has given us some pretty good information at the beginning, and that's it's being fired from this cannon, but so that means that our initial momentum was, again, equal to 0. So we know that the final momentum of the system also has to be equal to 0. So I'm going to do just what I did before. I'm going to figure out what the momentum of the known movement was, and I'm going to compare it to the unknown movement. So we know that the 100 kilogram clown was fired from the cannon at 15 meters per second. So that equals 1,500 newton seconds. So that means that if we're looking for the recoil speed of the cannon, the recoil speed of the cannon or the cannon itself had to have a value of negative 1500 newtons per second for its momentum. So I'm going to set that as negative 1500 newton seconds, and I'm going to just put in my mass once again, 500 kilograms, and then I'm going to figure out what my velocity was there. And so 1500 divided by 500 means that this is equal to 3.0 meters per second. And this would be in the, we're assuming, I guess, that this is moving in the right direction with the clown, and so it would be moving in the left direction with the cannon. They're obviously just looking for the magnitude, so we don't have to necessarily worry about the negative sign in this case. All right, so this next problem, it's also a fairly classic momentum problem. I have ball A of mass 5 kilograms moving at 20 meters per second, and it collides with ball B of unknown mass moving at 10 meters per second in the same direction. So I have ball A and ball B, and they're moving this way. Okay, now what's happening is that ball A is moving twice as fast as ball B, so it catches up with it and runs into it. After the collision, ball B has slowed down, it looks like, to 10 meters per second, and ball A, and then ball B has sped up to 15 meters per second, both in the same direction, and we want to know what the mass of ball B is. And so we're going to remember that we have our original momentum has to equal our final momentum. So what we can do is we can figure out, well, what's the total momentum originally of both ball A and ball B combined, and we'll make sure that that equals the final momentum of ball A and ball B combined. Okay, so let's see what kind of information we have here. We know that for ball A, we have 5 kilograms, and it's being multiplied by 20 meters per second. And then we also have ball B. Now we don't have all the information, but we have the mass B, which is what we're trying to figure out, times 10 meters per second. Okay, so there's our original information, this and this, and then we're going to say it's going to be equal to our final information, which is that ball A, this is now at 5 kilograms, and it is moving at 10 meters per second, so it's slowed down, while B is still unknown mass, but we know it's changed its velocity to 15 meters per second. Okay, now at this point, if your algebra skills are decent, you should be able to see that all we're really doing is just solving for a variable here. We're just solving for MB. So if we can get our numbers on one side and the variables on the other side, it should be a fairly straightforward problem. So right here I have 5 times 20. This is going to equal 100. This is just going to be MB 10. On this side I have 5 times 10, so I have 50. And this side I have MB 15. Okay, so let's see if we can combine a few terms here. We'll move the numbers over to this side, negative 50, negative 50. So I know that 50 plus MB 10 is equal to MB 15. Okay, so let's get the MB over the other side. I'll subtract this out on both sides. And we find out that 50 is equal to MB, 5, right? And then just divide out the 5. And so we know that the mass of B is equal to 10 kilograms. Okay, pretty straightforward, Matt. All right, so the last thing we'll do on conservation of momentum, we'll try one more, and this is a slight variation of what we've been doing, but it kind of works on the same idea of just remembering that our first momentum when we start, it should be equal to the momentum when we finish. And this is always pretty much true with momentum. As long as no outside forces are applied, that's really the key to solving these momentum problems. Just remembering that whatever you started with is what you should be ending with. Okay, so what do we have right here? The diagram below shows an 8 kilogram cart moving to the right at 4 meters per second to make a head-on collision with a 4 kilogram cart moving to the left at 6 meters per second. After the collision, the 4 kilogram cart moves to the right at 3 meters per second. What's the velocity of the 8 kilogram cart after the collision? And so I can kind of go through here and see what I have. I know that what I have going to the right for momentum is 8 kilograms, and it's moving at 4 meters per second, and it runs headlong into a cart that's moving in this direction. So why don't we do this? Why don't we say, since it's going right, we know that velocity going right gives me a positive number, and then so the momentum of the system, we can really subtract out this 6.0 meters per second and multiply that by 4 kilograms. I guess I kind of did that backwards a little bit there, right? And so we can say, well, this one is 32, this one is 24. So that means that after the collision, the 4 kilogram cart moves to the right at 3 meters per second. What's the velocity of the 8 kilogram cart, right? So if you take these two originals, since they're moving in this direction, this comes out to 32 minus 24. My momentum is 8 newtons per second. That means after it collides, the total collision also has to equal, the total momentum also has to equal 8 newtons per second. So what happens afterwards? After the collision, the 4 kilogram cart moves to the right at 3 meters per second. So 4 kilograms times 3 meters per second is equal to 12, okay? But I know that my system has to equal 8. So that means that the other cart has to equal -4. And so with that, I can just say, okay, well, if my momentum is -4, it has to equal my mass, which was 8 kilograms, times some unknown velocity. 4 divided by 8 is going to be equal to 0.5. And since it's going to be negative, it has to be moving to the left. Okay, so 0.5 meters per second to the left.